Hello, my name is Mario Duenas, and this is my Lab 5 report. For this lab, I decided to do the Slinky Drop, which was a preset video provided by the school. The purpose of this lab was to assess the vertical displacement of a slinky while being dropped, which would focus on the forces of the spring, tension caused by this force, and gravity and its effect on each section of the slinky in freefall. The applications used in this lab was GlowScript. I also wanted to use Tracker, but I could not find any information on the mass of the slinky used in the video, as well as the length initially. As shown in the video provided, a slinky drops in such a way that the bottom has no vertical displacement until the top part reaches it. This was shown in the coding model I created, as the slinky didn't displace at the bottom until fully compressed, creating an accurate model in that aspect. Because we lacked initial variables, I decided to use variables of my own. The mass of the slinky was 2.5 kilograms, while the initial position sat 10 meters above ground level. The initial velocity was also 0 meters per second since it was drawn from rest, and the spring constant was 40. I don't know if this is too much, but it worked in my model, so I kept it that way. The initial length was 1 meter, and then gravity, of course, is 9.8 meters per second squared. Some of the equations used was the force of spring, the force of gravity, and also a velocity update formula and the position update formula in accordance to Newton's second law. Now for the actual model, I wanted to assign mass to a helix, which would represent my slinky, but after some research, I found out you can't exactly add mass to these. I don't know why that's the case, but to solve this, I decided to put masses on the slinky, which would represent like sections of the slinky, and I chose more than one mass because in the real world, this mass would be distributed to each coil of the slinky, but on GlowScript, that isn't possible to do on helix. So I made a top mass, 3 masses in between, and then the bottom mass. And then I put in my initial conditions. And then I solved for the stretch at each section of the slinky. This would mean I needed 4 helixes between each 5 masses, or altogether. And then after this, I did my time loop, which would be first solving for the force of gravity, the forces of the spring on each section, and the masses below and above it. And then net force would simply be the addition of these forces. And then, of course, as we have been using in the lab, I updated position and velocity. And then I set it equal to the position of the slinky afterwards. So after all the time loop. The scenery and the graphs produced from the results of my model were also based on past lab experiments. And then in these results, you could see all 5 of the spheres. And then in the graph, you could see that the bottom of the slinky is not changing as time moves on in the y direction. It only changes about 0.55 seconds into the experiment, while the top mass is slowly going down and approaching the bottom. After this, they both fall down as they're both reaching the ground because of gravity. Some errors in this experiment, as you could see in the results, could be an impractical modeling that I produced. Theoretically, after the bottom starts moving, the top part of the slinky and the bottom part of the slinky should be moving at the same rate. And this is because the collision of the coils, since it's one body, it's basically perfectly inelastic in a way. And this isn't shown in here because on GlowScript, the coils don't have a thickness or a distance. I'm not sure how I would incorporate this so the computer could simulate the real world, but that idea would be present in the real world, I believe, but not present in the GlowScript model. A what-if question my experiment can answer is, what if a mass was attached to the bottom of the slinky? And this would result in a model that acts the same way, only the slinky now has more tension, so the length between each coil increases, but at the end of the day, the tension is equal to the force of gravity of the tennis ball. And what does it mean when the coils of the slinky collide when it compresses? Like I said before, it would be perfectly inelastic in a way since it's one body.